Okay, let's take a look at a second example for absolute max and minimum, or absolute extrema. We want to determine the absolute extrema for the following function on the interval -2 to 2. So again, we have a closed interval. Here's our function. F of x equals the absolute value of x cubed minus 3x squared plus 2x. So again, we need to find endpoints and critical points because those are the only possible places where we can have an absolute min or max. Now I want to talk a little bit more about that, why that is. Well, if you think about an absolute min or max, if it's the highest point on the graph and it's not an endpoint, then the function would have had to have changed direction. We talked about the fact that can only occur at a critical point. And the same for minimum, okay? If it's the lowest point on the graph and it's not an endpoint, it can only occur where the graph changes direction. So that's why we find critical points. That's why we find endpoints and we compare them. So let's take a look. Step one, we want to determine the endpoints. We're going to plug in -2 and 2 into this function. When we plug in -2 and take the absolute value, we get 24. So our left endpoint is -2, 24. When we plug in 2 and simplify that, we get 0. So our right endpoint is 2, 0. But remember, after we do that, we have to figure out the critical points. So I'm going to be taking the derivative to figure out my critical points. Now, what's the derivative of an absolute value function? Well, it's basically the absolute value of whatever you start with divided by that same thing without the absolute value, and then of course we have to multiply by the derivative of the inside. Now, there are times, actually, the way I said that, it actually works either way. Okay, let me talk about that. You can either put the absolute value bars on the top or bottom of your fraction when you take the derivative. It doesn't matter. So in other words, I could have put these absolute value bars on top and then left them out on the bottom, or vice versa. In this case, I just put them on the bottom. Again, it won't matter. That's because if the top is negative and the bottom is positive, you're going to get the same answers if the top is positive and the bottom is negative. In this case, I put the absolute value bars on the bottom, but we still have to multiply by the derivative of the inside, which is 3x squared minus 6x plus 2. So what do we end up with? Well, I guess that's why I put the absolute value bars on the bottom, because we just have plain factors on the top with an absolute value on the bottom. So here's our two factors on top. Here's our absolute value bar on the bottom for our derivative. And remember, critical points exist where the derivative equals 0 and where it doesn't exist. So the bottom we can see it can't be equal to 0, and the top will be equal to 0 when these two factors equal to 0. So we're going to have to factor these down even more, it looks like. So for the top, once we set it equal to 0, because that's where critical points occur, we're going to look at each individual factor. Our first factor, we can pull an x out of, and we're left with x squared minus 3x plus 2. Here's what our x is going to look like for the x method. It's going to factor down according to these two numbers on the left and right of our x. We have to pull this x down that you originally pulled out. So it's going to become x minus 2, x minus 1, and we have 3 critical values just for that one factor, this one factor. Okay, so the 3 critical values it generated are 0, 2, and 1. Now we have to figure out the critical values for our other 3x squared minus 6x plus 2, because that could be equal to 0 as well. We cannot use the x method for it, so we're going to have to use a quadratic formula. Here's our a, 3. Here's our b, -6. Here's our c, 2. We're going to plug that into the quadratic formula and figure out what x can be equal to. Simplifying it down, we get 6 plus or minus the square root of 12 over 6. We will break that down even further. Square root of 12 breaks down to square root of 4 times square root of 3, which is 2 square root of 3. So then we get 1. We can divide each of these by 6, right? So we get 6 divided by 6 is 1. 2 divided by 6 is 1/3. So we get 1 plus or minus 1/3 square root of 3. Now, one critical value would be 1 plus 1/3 square root of 3, which is approximately 1.577 when we plug it to the calculator. The other critical value will be 1 minus 1/3 square root of 3, which is approximately 0.423. So we generated 2 more additional critical values from this factor. So we generated 3 from this one, which were these 3, and we generated 2 from this one, which are the 2 decimals we just figured out. So that's when the derivative equals 0. Okay, we are going to plug those back in to figure out points. Now I want to mention real quick, what about where the denominator equals 0? Well, for an absolute value function, this is exactly the same as this, so it's going to generate the same critical values when I set it equal to 0. Okay, so we've got our 5 critical values. We're going to figure out our critical points. We're going to plug this back into the original, so I'm going to plug in my first critical value, 0, back into the original function. I get 0, so that's my first critical point, 0, 0. I'm going to plug in my next critical value of 1 back into the original. I get 0 back, so my next critical point is 1, 0. I'm going to plug my third critical value back in 2. I get 0 back for it as well. So my third critical point is 2, 0. My next critical point I'm going to plug back in to the original, and I am going to plug in this particular x, my more accurate x critical value, back into the original to make sure I get an accurate y value back around to 3 decimal places. So my next critical point is 1.577, negative 0.385. And I think what I did here was, next I plugged in the 1 minus 1/3 square root of 3 into my original function to get my other critical value, which is 0.423, basically the same as this rounded, 3.85, 0.385. So I've got 5 total critical points. All right, and again, this is pretty much how you plug into your calculator. Make sure you use parentheses correctly and all that. So here are all of my critical points and endpoints on a chart. So for step 3, just draw your point chart. Remember, your top row is going to be your left endpoint, your bottom is going to be your right endpoint. All of the rows in between are going to be your critical points. I feel like I thought I found 5 critical points. Let me go back and make sure I didn't miss one. Okay, that's why. This 2, 0, I do want to point this out. A critical point can be an endpoint. And that's important that you actually do that, that you plug in, that you include that in your chart. And they do overlap in this case, okay? But always check your left and right endpoints to see if they're critical points. So in this case, it does actually happen to be the same. So this endpoint is also a critical point, and there can be some overlap there. So now that we've drawn our endpoint and critical point chart, we just want to see which of these y values is the smallest and which one's the biggest. So let's take a look. Step 4, compare function values. Well, 3 of these share the tie of being the smallest value of 0. So all 3 of these are going to be absolute minimum. Okay, and I don't know why I didn't label that, but all these are going to be minimums. Not the ones in between here, but these 3 that are circled are going to be minimum. And this one up here is going to be our max because it has the biggest y value of 24. So let's answer with a reason. Okay, out of all the critical and endpoints, 0, 0, 1, 0, and 2, 0 had the lowest function values, therefore they are absolute minimums. And out of all of the critical and endpoints, negative 2, 24 had the highest function value, therefore it is the absolute maximum. So let's take a look at this function. We can see that these 3 points down here, and I'm not sure why the third one wasn't shaded in, all had the same y value of 0, and therefore these are all absolute minimums. Okay, and our left endpoint ended up being the highest, had the highest or biggest y value, so it's absolute max. So again, part of the reason we did this is because we can see that sometimes you have multiple absolute mins or multiple absolute maximums. In this case, we had multiple absolute minimums, one absolute max. And again, endpoints are very important because sometimes they take on absolute extreme values. All right, that's it for this example of finding absolute min and max on a closed interval. If you have any other questions about it, let me know.